Hello and welcome everybody to day 4 of OptiWave's webinar week. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave. I'll be helping out your host, Ahmed Attia. This webinar is going to focus on advanced applications using OptiSystem. And as with previous sessions, we will launch 3 polls that we'd like you all to vote on. We'll also have 2 Q&A periods at the halfway mark and at the end, so you can ask your questions at those 2 sessions. And next, we also have a handout available that you'll see on the GoToWebinar control panel. Feel free to download this handout at any time. And finally, this webinar will be recorded and distributed to everybody that registered. It will be delivered via email tomorrow at 10 a.m. Eastern Standard Time. Now that we got all the formalities out of the way, it's time to start the webinar. So I'll hand you over to your host, our Director of Optical Systems, Ahmed Attia.
Okay, good morning, everyone. Again, welcome to this webinar on OptiSystem. Today's webinar would be about advanced applications, and we're mainly going to talk about the following topics. Going to give you some introduction about the applications we're going to talk about today, mainly about binary BSK, using ReadSolomon encoding, and how to generate waterfall curves, BR waterfall curves, using scripting. Then during the presentation, we're going to describe the different components used in this project, and which includes the forward error correction encoder and decoder, the pulse generator for binary BSK generator, and then the bit error set used in the project, and then the decision component, and then run the project and do some component description. And finally, we will calculate the project and show you how the results are stored in an Excel spreadsheet and it's calculated. Then finally, we end up with a few questions and answers. So mainly the main idea behind this webinar is to create the bit error rate or simple error rate, depends on the modulation scheme you're using, waterfall curves, and typically in industry or analysis, the waterfall curves are used to characterize the performance of the communication systems, where you map basically the bit error rate versus a metric of the signal. This metric could be either a power level of the received signal, or could be a signal to noise ratio. If it is optical signal, you have optical signal to noise ratio, or could be electrical signal to noise ratio, or you may have the bit error rate versus energy per bit to noise energy or noise density. Now, the concept of noise density, you might have it in the literature as defined noise spectral density, sometimes noise power density, or just noise density. Typically, it's the N-node parameter, which is measured in watt per hertz. And in our example here, we're going to use an additive white Gaussian noise generator to add to the signal, basically, and to create the noise level in the signal. In principle, the additive white Gaussian noise has a power spectral density which is flat across the frequency. That's why we call it white, and it has the level which is N-node over 2. Now, if you look at the noise, we call it additive because it's directly linearly added to the signal. The autocorrelation function of the noise is a delta function, which is at 0. And its value in N-node over 2. The example which we're going to study today, go over it today, is the binary BSK with the ReadSolomon encoding. The example basically have the phase shift keying signal generated and code added to it using a forward error correction code component, which is the encoder here. And so the encoder
basically we have here the bit test set. We're going to talk about it in more details later on. But this bit test here, it generates the pseudo-random bit sequence. It's built in it, the pseudo-random bit sequence generator, and it generates the random sequence, which is for us is the information. We add up to it the redundant bits to create the error correcting code using the ReadSolomon code, and then basically we pass it through the pulse generator, which is in our situation here is the phase shift keying generator, and then we add up to it noise linearly, as you see here. This is the additive white Gaussian noise, and then pass it through to a decision circuitry, and then the decoder, and then we have passed the signal back to the bit error rate tester, so to be able to calculate the bit error rate. Or in our situation, and if you have different kind of modulation here, you can get, for example, symbol error rate. Now, the system, we're going to look at it here. We're going to look at 10 gigabit per second system, and we're going to look at single polarization. So it's the polarization, you can single polarization or dual polarization. This is the capability of the component. You can set it up in here in the system, and also additive white Gaussian noise. Now, if you look at the library, which is part of the documentation, you're going to see under the advanced modulation system examples, some example which we calculate symbol error rate and bit error rate for different modulation schemes, including different kinds of QAM or BAMs or QBSKs and PSK, different types of it. All of these examples are similar to the example we're going to describe here, which is the binary phase shift keying. So the concept which we are talking about right today is applying for all these kind of schemes. Okay. Here we're going to talk about the ReadSolomon coding, and basically the ReadSolomon coding is a cyclic code which we take the information bits, we add to it redundant bits, and these redundant bits they create new symbols, and these symbols will have a certain number of bits. In ReadSolomon code, the number of bits are defined as M, and the code is defined with indices N and K. Now, N represents the total number of code symbols, and the K represents the total number of information symbols. And typically, for example, there is different types of ReadSolomon codes. Some of it's like 255, 247. So if it's N is 255, so you have total of 255 code symbols and 247 coded symbols. Now, the difference between them is eight symbols, which is like basically you can represent them with 2 bits or 3 bits, redundant bits into the code. Now, if you look at the pictograph here, basically you have information bits, which is generated by your source, and then you add up the redundant bits to create a coded symbol. And this symbol, we have 255 of them. Now, these symbols, you have K information symbols again, and then N minus K redundant symbols, which in our situation have 8 redundant symbols. Now, these codes, the ReadSolomon codes, if you look at the error capability, correcting capability of the code, we define a parameter which is called T, and this T is equals to N minus K over 2. So in our situation here, you have 255 minus 247 is 8 divided by 2, 4. So this code, the ReadSolomon code RS 255 247, is capable of correcting up to 4 symbols errors. And now depends on now each symbol, as we said earlier, is 8 bits. So total of 32 bits you can correct. Now depends on the location of these errors in the received code. If they are consecutive errors, then you should be able to correct up to 32 bits. However, if you have these errors are located across more than 4 symbols, let's say for example 5 symbols, so the maximum number of errors we can correct is defined by the formula, which is given by T minus 1 times m plus 1. So for example, our case here, we have 8 divided by 2, which is 4. 4 minus 3 is 3. 4 minus 1 is 3. 3 times 8 is 24 plus 1. So this code is capable of correcting maximum of 25 errors located across five symbols. Okay, now because of the addition of these redundant bits into the information bits, the number of sequence bits which is exiting the forward error correcting encoder typically has to be larger than the number of bits entering the redundant symbols. And depending on the code we are using, the ReadSolomon code, we are using basically the number of sequence bits would be larger or lower. So in the examples here, we have different types of ReadSolomon codes, which is RS-255, 247, which we mentioned earlier. We call it in RS, or it's known also RS4. There is other type, which is like 255, 239, which is known as RS8. And there is also RS-255, 223, which is known as RS16. Now, in the component description, we're going to show you later on, you can set this, and this is through the component properties of the FIC and encoder and decoder. Now, there is another feature of these encoders we're going to use today in the example. This feature is called trim to sequence length. Now, this feature, what it does do is basically controls the number of bit sequences exiting the encoder, because we typically have more bits coming out of the encoder compared to what is coming in. But with this feature, if you enable it, you should get the same number of bits at the output. This kind of application typically used for high-order advanced modulation schemes. And the number of symbols typically, again, if it goes out of the decoder, it has to be, again, equals to the number of bits which is coming into the encoder. Now, the symbols which are not decoded, there will be some number of symbols which not decoded correctly, and this will be discarded in the bit error rate tester. Now, talking about the components which we're going to use in this project, the first one is the pulse code phase shift keying pulse generator. And the component itself, it has two outputs, which is used for emery or other types of modulation schemes. So two parallel emery electrical signals. Now, in our case here, we're going to use only one of them, because we're going to use binary BSK. So we have 2 bits, 0 and 1, and these bits will have phases. In our case here, we're going to have 0, 4, and pi. The bit error, the other component we're going to use here again is the bit error rate test set, which generates a large number of bit sequences. Now, this device, you have 3 options in it. You can either use the internal built-in random bit sequence generator in this component, or you might use an external bit sequence component, which is in the library of OptiSystem, or even you can load your own bit sequence. So if you have, for example, a certain random file you wanted to launch into the experiment or the project you wanted to simulate, so you can do that using the external defined file feature. Okay. Now, the decision component used in the project does do a soft decision on the received symbols based on the threshold setting. And the main functions of this component is, first thing is it blocks the DC component in the signal, and then do some kind of normalization, and then calculate the error vector magnitude, and then decide make a decision on the received signal. Again, the noise which we use here is generated by additive white Gaussian noise with power density in node. Okay. Now, the project which we're gonna do right now, we're gonna just give you a brief description before we go to the project layout, but the things which we need to do here, we're going to go through the component, each component, and look at the parameters setting for these components, and we go through the script used for this project. Now, the script here, my colleague yesterday gave you or mentioned that the scripting of the used in OptiSystem. We're going to talk about it also here briefly today after the break, and then we run the project and start to getting the waterfall bit error curve. So I'm going to take a break here actually, and my colleague will run the second poll, and then we continue afterwards doing the project. Thank you very much.
Thanks, Ahmed. Second poll is up for everybody. Please take a second to answer it. And if you have any questions, please go ahead and type them out now for Ahmed to take a look at. And we have one more follow-up webinar session for OptiSystem. It's tomorrow, I believe at the same time. Let me just double check. Yeah, so it'll be same time tomorrow with, again, an extension of the advanced applications that we're doing today. So if you haven't registered, do that. I'm going to give it a couple more seconds for some questions to come in. Okay, I'm going to go ahead and close the poll. Doesn't look like we have too many questions that can be answered right now that just came in, so I believe Ahmed will probably just go ahead with the rest of the presentation.
Okay, thanks, Brian. Okay, now we're going to go into the project layout and the script of it. So again, the project is designed here for a binary BSK. If you go to the library, which I mentioned earlier, you can go for other examples using for QAM, for PAM, and other modulation schemes. The main component here, as you see, is the here initially the bit error rate tester. If you click on it, you're going to see the polarization here. State we're going to use single polarization. The bit rate here, which is, if you see, it's a script based on bit rate. Now, if you do evaluation of the script, it tells you the bit error rate is 10 gigabit per second, and the order of the random bit sequence generator would be 16. If you close here and you go to component layout, you can see the bit rate is defined as 10 gigabit per second. The sampling samples per bit is 64. The sequence length here used is 65,536, which is 2 to the power 16. And then in the setting here, you're going to see the ReadSolomon index N and ReadSolomon index K. In our situation here is 255, 235. One thing we need to know is the script is right now is written in a way that it will do single ReadSolomon curve at a time. So if you need to run the other curves in the ReadSolomon code here, then you need to change every time. You need to change the indices and then run the script and then get the results, and the Excel spreadsheet will be updated based on the new settings. Okay, so the other component, which is going back again to the bit error tester, you can see the noise here. In the tab enhanced, we have the bit error bit sequence generator, which is internally used, and which the order. So the order, as we said here, is 16. If you evaluate the script, and the order is generated through this function, and basically we generate random seed here as well in the noise for the system. Now, if you go to the second component, which is the forward error correction code, again we use the indices which is set in the global parameter as a script here, as you see, and we press enable. It means we're gonna enable forward error correction. So if we want to do no correction in the transmission, so we have to disable here and run without the error correction in the example. This is the fork, which is basically splitter, and then here the pulse generator, which is the phase shift keying. We are using here 1 bit per symbol, so because it's binary, BSK, so we have only 2 phases. Now, if you use a QAM or you're going to use QBSK or any other schemes, the number of bits per symbol depends on the modulation you use. So, for example, if you use a QAM, QBSK, then you have 2 bits per symbol. And now this is the phase offset initially. So if we have, in our situation here, as we mentioned earlier, we have 2 phases, 0 and pi. If you wanted to make offset here, let's say 40 degrees or whatever, this is used in QAM applications and in other higher order modulation of PSK. Then you can choose an offset here by a certain amount of degrees and then run it. This part is the additive white Gaussian noise, and here is the noise power given in this example. You may be able to set it as power spectral density value or a noise power value, so you have 2 options. Now, this component is the decision component, and in it you have defined the different parameters. You have to copy them from basically the scheme here. So you have binary BSK, you have single polarization, you script the reference bitrate, and so on. This is the decoder, the BSK decoder, which is opposite the other device, and this is the FEC decoder, which is also, it has to be defined in the same scenario here. You have to enable it or disable it and choose the script of the indices of the ReadSolomon sequences. Now, the project here, basically, when we wanted to run it, you may run it 2 ways. You can run it the regular way, which you have the project layout here, and then you run it. Once you run it, you will not run the script designed for this this project. So this is the script. If you press on the script tab here, you're going to have the script here. The script, most of the scripting language here can be used as a basis for writing scripts in the future. So every statement here has its own description, so it's easy to understand. Here you can see that the way how the files are read from certain directories, how the data would be placed when it is outputted from the calculation, and so on. Also here, if you can see, this parameter is called enter BER equals 5. This is the number of times of repeat of BER calculation per bit error rate, energy per bit to noise level density. So if you want, for example, to have more, again, if you remember, we said yesterday about, or the day before, about the randomness of the calculation and the difference performance from trial from run to run. So to average that, you may increase this number to kind of getting more average value for the run. So again, you can run the project through here to calculate, and would be only doing the parameters which is set up here, or you can run it from script. You go to script here and then press run. Once you run it, you're gonna execute the commands which is in the code, and go through the process of collecting data and storing the data. Now the program to run it right now, the script to run it takes about 8 minutes. So I'm gonna run it and go back again to the presentation and give more details about the example here. So, and we come back again to it later on. So if you run here, you're gonna start getting this window, and basically if you can get this window here, pop-up window which says calculating signal to noise ratio per symbol iteration, which is 1 out of 20, and this is calculation. As we said, we have 5 sweeps every time, so has to go through 5 calculations and then average out the calculation. So again, it's going to go over all of these settings. If you remember, we had the FEC here is the ReadSolomon 4 code. So if you go to Excel spreadsheet here, the file starts to fill up the parameters. Here it's already pre-filled, but it's gonna put the new data into it every time calculation. So here first value is 0, now it fill it up, and so on. What you will have eventually when you run over all the simulations, you're gonna have the ReadSolomon 4. So you have to change again the settings in the global parameter to the different ReadSolomon coding, and then eventually you're gonna get the curves for the different coding schemes. And you have also, you have to set at some point the situation with, you have no FIC here and you have theory bit error rate. So you compare all these curves together, and then you have one single output curves, waterfall curves for this example. In the library, which I mentioned to you earlier, you might have exactly the same example for QAM, for BAM signals. Okay. Now, if you go through the theory of the calculation, it's based on the following equations here. In our situation here, we're going to use the bit error rate because we use binary. If you have more QBSK, for example, you can use the symbol error rate equation, which is defined in this here. And in our situation here, m equal 2, you might have m equals 4 in QAM, and so on. Okay. Now, in this kind of calculation, which we do, if you need to improve the bit error rate results, you have to look into the case where you do the calculation. So if you have, for example, low error counts, which means you have high signal levels compared to noise levels, then, or you might have, for example, strong FIC, which is like ReadSolomon 16, then in that case, you might need to increase the parameter, which is the sweep number. And also you might need to increase the sequence length. Now this, when you do that, basically what's happened is your simulation time will go up, but eventually you're gonna get better performance into the final results. Okay, the other thing is in the components which is used here, we have an oscilloscope, which is a visualizer in the oscilloscope, and the oscilloscope has a script in it which it will enable it to calculate the noise variance. Now this noise variance is used in the script to be able to calculate recalculate the noise level, and this noise level will be imported to the calculation and used for normalization processes and comparison. Again, as we mentioned earlier, the FIC decoder, because it removes the redundant symbols, you have the sequence number of bits will be different than the original sequence of the bit error tester, which is sent, and that is normal, and you can see that when you look into basically the code, and if you monitor, for example, every iteration of the bit error calculation, you can see that the number is adjusted, and the bit error tester will ignore all the not unknown or unused symbols. Okay, so this is just to show you here in this slide the script which is used for the oscilloscope component. Then how this component will be used to generate the noise level, basically, which you calibrate the noise level of the additive wide Gaussian noise. Okay, so I'm going to go back again to the calculation, and you can see this is still running now, the calculations. So eventually, what we're going to have, it's going to take a few more minutes to do that. You have here in the directory, you might have the curves, which is basically the curve for everyone. So here, I'm going to show you for example, the example for the QAM. So the QAM, you have 32 QAM, 16 QAM, 32, 64, 128 QAMs comparisons, and you can look at the curves for the different types of modulation schemes using quadrature amplitude modulation between values between theory and between calculation and the used equation for the theory is defined in here in the file, in the Excel file. If you look at the different types of phase shift keying, you have QBSK, you have 8BSK, 16BSK. Also the same scenario, you can have the different curves. And these changes we are seeing here is because of the calculation I'm running it right now. So it's kind of because it's stored in the file. So I think I'm gonna do is I'm gonna stop the calculation. And finally, for example, here for pulse amplitude modulation example also, you might have different curves for each modulation. So you have amplitude shift keying, which is BAM2, and then BAM4, BAM8, and so on. Okay. So going back again to the presentation, with this, basically what you need to do is you need to make sure that the script which is used, let me go here again. Hopefully this is logged off. Okay. So still running. So I'm trying to close it, but it's fine. Okay, so anyway, so with this, if you run the script in these examples, you should be able to use the script for any kind of project you need to create waterfall curves and create performance analysis for the communication system. With this, I conclude the presentation. We're going to do the third poll and try to answer questions on the provided by you guys. Thanks very much for listening.
Thanks a lot, Ahmed. I went ahead and launched the third poll, and we've been getting quite a few questions just yesterday and today regarding the material, like the handouts that were available in previous sessions. I don't think there's any way that they're made available via GoToWebinar after the session ends. So what I've been recommending everybody to do is to simply email support@optiwave.com. You'll have to specify which session you're referring to that you'd like the materials for. But if you just email the presenter, basically, you will be able to get the materials afterwards. You can just email it to you. I might put a page together with all the materials afterwards. I haven't thought about doing that yet, but it looks like that might be something of interest for everybody. But yeah, just email support@optiwave.com. Put the session that you're looking for, so like OptiSystem advanced features or OptiSystem advanced applications. Just let us know that you want the material, and we'll go ahead and email that to you. We are getting a couple questions in, so I'll go ahead and close the poll and pass the mic back over to Ahmed.
Thanks, Brian. Actually, the question which I have so far is I'm gonna do the answer to them directly because they are kind of questions related to integration of the software with other types of softwares, and the other question is related to the material, which, as you said, we will give this presentation, and the material will be available on the website to all attendants. Thinking is with this we can conclude the webinar, and thanks very much for everyone attending today. Tomorrow our webinar would be about applications for using the OptiSystem to analyze Raman amplification in WDM systems, and how to set up the parameters for using the Raman in the optical communication systems. Thanks very much for listening today. Bye-bye.